Welcome to PyData Global 2024. I'd like to welcome you to Sergey Maydanov's talk. He's a senior software engineering manager at NVIDIA, and we'll be talking on the nvmath-python, bringing NVIDIA math libraries to Python scientific community. Thank you so much, and I'll let you take over from here.
Thank you, Stephen, for introduction. Good morning, good afternoon, everyone, and maybe good night for some of you. I'm excited to be with PyData Global and present the new Python math library, which is called nvmath-python. And we'll spend about 30 minutes today digging into what it is and why it is. I will start with explaining the motivation why we need yet another math library. And then we'll go through core design principles of this library. And then we will summarize the nvmath-python architecture. I will talk a little bit about the roadmap, and we'll have a summary and call to actions with some Q&A afterwards. So why do we need nvmath-python? Why we need yet another math library? So technically it is a math library, but not exactly the library. It's based on existing NVIDIA math libraries. And in the past few years, we were reimagining our CUDA math libraries, including adding capabilities for just-in-time compilation of these libraries. Just imagine QFFT. On the surface, it looks like a regular math library, but under the hood, it uses JIT compilation technology. When you can select the problem, the data types, the algorithm type, and actually add some custom user code. Well, when it comes to bringing these capabilities to Python, one of challenges that people will face is how to express this user-defined code. And in traditional way, it's been expressed as a CUDA strings, which is not always welcome in Python community. Some of Python users, they know Python, they don't know CUDA, etc. So nvmath-python is bringing these capabilities, but in Pythonic way. So on the right-hand side, you can see that we can define a regular Python function and supply this function to the library and compile it on the fly using JIT technologies. In our case, under the hood of nvmath-python, there will be invocation of number, and number will compile this code into intermediate representation, which then will be fused together with other FFT kernels. That's really exciting technology. So technically it's a library, but not a library. It's a library and a compiler mixed together. Another motivation, many of existing math libraries, they follow NumPy APIs, which is great. NumPy is a great library, but sometimes it leads to suboptimal performance. I'm giving an example from linear algebra, and sometimes we need to perform operations like matrix multiplication, then adding some bias. If you're in deep learning space, you likely apply some activation function like RealU. So technically, you can implement everything using NumPy-like approach, but the performance will be suboptimal because you will have multiple kernel invocations. In our case, it will be invocation of matmul, then plus C, then RealU implementation. So everything will be associated with extra overheads related to kernel submission, related to additional memory trips. NVIDIA math libraries like Q+LT or Q+DX. They provide advanced matrix multiplication APIs to cover these more extensive advanced scenarios. In particular, we can perform A times B plus C and apply epilogues, in our case, predefined real U epilogue. On the fly, and again, using JIT compilation technology, we can fuse everything together in a single kernel with amazing performance. In Python, you can reach 90% and even greater performance peak of respective hardware. Okay. One more motivation. Now, suppose you want to write a device kernel. And traditionally, you write device kernels using C++ APIs. But thanks to Numba compiler, you can do the same thing, staying with Pythonic toolchain. And if you're familiar with SIMT programming, then you can seamlessly implement such a kernel using Numba. I'm excited to announce that we are now providing even simpler programming model with Warp language. It recently added a tile programming paradigm, and you see implementing the same code is much more compact. So the bottom line, you have a choice of technologies. You can stay with CUDA, you can use Numba, you can use Warp, and implement device kernels which contain mass library calls. And again, thanks to JIT compilation, everything will be fused into a single kernel, giving you close to ideal, close to peak performance. Okay. Let me spend a few moments on explaining core design principles behind this library. And as you noted, one of foundations for this library design is be Pythonic. Avoid C++ as much as possible. Actually, all APIs are truly Pythonic, high level. Second design principle is this library is intended for performance and scalability. And the motivation for that, as long as you can deliver optimal performance, you don't need to go to native languages. That's one of our core promises. So when you need to go to extreme performance, nvmath-python would probably be one of your top considerations for that. Second idea is when you start coding, you typically start prototyping on laptop device, on notebooks, maybe even on CPU, and then later gradually migrate this code to GPU. It can be a discrete card on your notebook, or you can scale it to server, which has more powerful CPU and GPU. The promise here is that with very modest code changes, you can implement both CPU and GPU code and seamlessly migrate. And on every migration step, you will get performance close to peak on a given hardware, on CPU or on GPU. And on the right-hand side, you can see that it can even scale to multiple GPUs, multiple nodes, where we are soon introducing the distributed APIs, which allow you to work with different distributed libraries, such as MPI for Pi, or you can use Dask to scale your computations to many GPUs, many nodes. Okay. Another core design principle is trying to separate execution stage from planning and auto-tuning stage. And for this reason, we provide so-called object APIs, or in other words, we provide stateful APIs. Actually, we provide both stateless and stateful APIs. The stateless API is for expressiveness. It's just single line API, which allows you to compute like A times B and get the result in an array, in a tensor array. It's a like function style API. Stateful API is object API. You instead create matmul object A and B and store this object as MM, and then you can play with fields of MM. You can do extra auto-tuning. You can do extra logging, debugging with that. So we have logical separation of different stages, and it allows to amortize some one-time planning costs. And if you have some batch computing of many matrices, you do planning once and then compute many times. And this way you amortize these expenses. The last but not least, we don't want this library to be a black box. So we provide integration with standard Python logging capabilities. So you have full control of what's going on under the hood of this library, how the planning was done, what kernel was selected, which is useful for debugging and other purposes. Okay. One more significant design consideration is interoperability. In many ways, we do not want to reinvent the wheels. We do not want to create a universe around nvmath-python. Instead, we want to be part of existing ecosystem. The whole motivation, people already using tons of great packages, tensor libraries. We want nvmath-python to work within this ecosystem rather than force people to re-implement their codes with nvmath-python. So under the hood, we provide zero-copy data interchange capabilities through array interfaces, DLPAC. So nvmath-python can work with CuPy tensors, with NumPy tensors, with storage tensors. This is exactly what you need to integrate nvmath-python into existing workflow. And the second bullet point is nvmath-python integrates with popular JIT compilers. JIT compilation is in the essence of nvmath-python. So we provide full integration with Numba, with Warp, and in future with other JIT compilers, so that you can implement device kernels using nvmath calls seamlessly. Okay. The last but not least, we want nvmath-python to be a first-class citizen of Conda and pip ecosystem. And you can see multiple ways how you install nvmath-python. You can install nvmath-python along with CUDA 11 or CUDA 12. If you want to extend nvmath-python with device capabilities, you will want to install DX library stuff. If you want nvmath-python to support CPU execution space, which is a new addition to the library, you specify CPU. And same works for both for pip and Conda. All right. Now let me summarize how it looks like from the architectural standpoint. On the very bottom, you can find that there is a lot of goodness coming from existing CUDA-math libraries. On GPU side, it's QBLAS LT, QBLAS DX, QFFT, QFFT DX, and other libraries, solvers, etc., etc., etc. We also have CPU libraries on AR64 side. We provide optimized NVPL library. So when you have a CPU execution space on ARM, it will invoke NVPL. If you're using x86 host, our APIs will be executed and accelerated using MKL library. On top of these native libraries, we're providing thin layer with low-level Python bindings, which may be useful for other packages, other libraries to integrate nvmath-python capabilities on low level. For people who do not want to deal with native stuff, who want to use Pythonic APIs, but still relatively low level. An example can be QPy community wants to rely on some of nvmath capabilities rather than maintaining CUDA stack. That's perfectly fine to use low-level bindings from nvmath-python to implement some of QPy functionality. Second, on top of these low-level bindings, we are providing truly Pythonic high-level APIs. They're not necessarily following NumPy, SciPy APIs, but they're expressive enough so that researchers, scientists, they understand typical operations. They're natural. These APIs, like we saw, they're organized in three different blocks. There are solely host APIs. Basically, this is APIs that are invoked from the host and do not require anything else from you. There are also certain APIs, like we saw in math-model epilogues or FFT callbacks, that use device callbacks. And some of these device callbacks, they are expressed using number or word. This is where we need tight integration with respective JIT compilers, number, word, and in the future, some other JIT compiler technologies. And there are truly device APIs for nvmath-python. This is useful when you use nvmath-python calls from within JIT region when you implement a fused device kernel. And again, for truly device APIs, it's tightly integrated with respective JIT compilers, so you compile and fuse everything on the fly. And on top of that, we interoperate with tons of other packages with existing Python ecosystem with NumPy, SciPy, QPy, Torch, and other popular libraries. All right. The roadmap. This is very new product and project, and we had very first release in July of this year. We initially provided a subset of host and device APIs, showcasing advanced matrix multiplication capabilities and FFTs, and provided JIT compilation using number. Recently, actually, a few weeks ago, we had second release, and in this release, we extended library capabilities to provide CPU execution space. You now can seamlessly switch between CPU and GPU, or actually implement workflows that require both CPU and GPU computation. We added random number generator capabilities for device APIs. So now you can use number with nvmath-python RNGs to implement something like Monte Carlo simulation kernels for GPUs. It was great work together with Warp language team, who recently implemented tile programming using Warp. Really nice, simple, expressive programming model. And we provide respective nvmath capabilities, so you can implement tile programming kernels with Warp and provide calls to matmul or FFT from within that kernel. And we recently had announcement of proof of concept implementation of multi-GPU, multi-node capabilities in nvmath-python. We demonstrated on a supercomputing conference that multi-dimensional FFTs from nvmath-python can scale to thousands and thousands of GPUs. In terms of future work, actually a lot of things, good things to do for us in coming year. We're focusing on implementing sparsity support, sparse format, both structured and unstructured sparsity, and leverage existing native library capabilities for that. Stay tuned. We will add more dense and sparse solvers in the year, and we'll productize multi-GPU, multi-node capabilities support. All right. Let me summarize. So nvmath-python, you can think of the library as an attempt to reimagine Python math libraries, how to bring existing C++ header-only library capabilities or JIT compiler capabilities from native libraries to Python space in Pythonic way, and yet achieve best performance, actually close to peak performance, allow integration with known just-in-time compilers, with popular compilers like Numba and Warp. We follow certain design principles that allow this library to be Pythonic. It's open source. It lives on GitHub. We focus on performance and scalability, but yet we do not want major code rewrite to be associated with each migration deployment stage. And we want this to be seamlessly done on both GPU and CPU. We provide stateful and stateless APIs for greatest flexibility when you want to use functional API. When you want greater control, you use stateful APIs. And we provide interoperability with existing ecosystem. We provide Conda and pip packages. On architecture side, we leverage native math libraries for greatest performance, but also leverage existing popular tensor libraries and frameworks. We interoperate with them in effective way. We rely on native capabilities for just-in-time compilation through NVRTC stack, but also on Python side, we leverage Numba and Warp, and we provide low-level Python bindings together with high-level APIs. In terms of roadmap, like I said, it's available as Conda and pip. It's available on GitHub. We just released beta. Very excited about these new capabilities. Try it out and stay tuned for 2025. And now I am open for questions, if any. Thank you. Okay, one question on slide 5, is an import needed for using warp.kernel? Yes, to save some space on the slide, I didn't include import statements, but yes, you need to import warp as WP. One more question is interoperability with TensorFlow provided expected? It's not yet provided. I think interoperability in terms of can I use TensorFlow tensors? Yes, nvmath-python supports DLPAC protocols. Technically, you can use TensorFlow tensors and pass this to nvmath-python through DLPAC. All right. Any final questions? Well, it's been my pleasure presenting nvmath-python to PyData Global. PyData is the first conference I attended starting working on Python about 10 years ago. And this is one of my favorite conferences. Thank you everyone for attending. We'll be happy to chat with you offline, online, in person. Thank you. Bye.